Good morning again. It's about 11:32. I think we can start. It's my pleasure to introduce Dr. Dave Page today, who is going to give us the SAM talk. For those who do not know, the Regenstrief Institute SAM talk series was named for the Institute founder, Sam Regenstrief. The talks are for speakers who are known nationally, internationally within the topics that are related to our RI community. We try to bring researchers who are multidisciplinary, involving clinicians, PhD educators, staff, plus someone who has achieved a lot in their fields and can share with us their knowledge and their insight in particular topics. Today, as I mentioned before, it's my pleasure to introduce you to Dr. Dave Page, who is a professor in chair of biostatistics and bioinformatics at Duke University. I had a pleasure to work with David at University of Wisconsin-Madison for several years, and it's great to have him here today to speak with us. David's work focus on machine learning, data mining, and building algorithms, then applications to using biomedical data and trying to use electronic health records, doing high throughput genetic and other molecular data. David's interest in machine learning is on complex multi-relational data. He works with electronic health records, as I mentioned, and molecular data. David has an impressive amount of publications out there. He has been given several awards, and more recently, he was named as a fellow of the American Academy of Medical Informatics. So David, welcome, and we are really looking forward to hear what you have to share with us today. Appreciate you coming.
Thank you so much, Anita. It's really an honor to speak to this group today. Thank you very much. Hi, Umberto. Let me see if I can successfully share my screen again. There it is. Okay, it's in a different color this time than it was before. It's trying to.
He always tries to trick us, David.
There we go. I hope everyone is seeing my title slide here. Please interrupt me at any point. Just unmute and ask me a question if you want to. Anita, maybe I'll ask you. I'm terrible at monitoring chat while I'm speaking, so if something pops up in chat, please let me know. But feel free to ask me questions. I think the first 8 or 10 slides will be just kind of helping us all be in agreement. I think many of you are also working on machine learning from electronic health records, but I'll give a little bit of background and motivation and then jump into some details. In case I don't get through all the slides, I only have 40 slides. I don't think it'll be a problem, but if we have opportunities for discussion and you ask me questions, that's great. If I don't get all the way through, I want to go ahead and just do my acknowledgement slide up front. Especially the first 4 people that I name here. I'll be talking about a lot of their work. Mian Wei is a graduate student working with me here at Duke. Xiaowan Huang is the last of my PhD students at Wisconsin. He'll be finishing up in another month. And Ross and Charles were 2 of my students who finished not too long ago at Wisconsin. Again, probably you're all in complete agreement with the motivations that I have, but let me go over some of them. If we had had electronic health records, and I think Regenstrief did, but most of us didn't back in the 90s, you might have looked at my record and seen some information such as this, and you might have seen me come in with elevated blood pressure and some occasional PVCs or heart palpitations. And it would have been really great if you'd looked at that and told me the next time that I came in, I'd come in with atrial fibrillation, which is the most common form of irregular heartbeat or cardiac arrhythmia, but it's not real common in 34-year-olds, which is when I had it. And it would have been great if you could have told me ahead of time, and I could have taken a few weeks of vacation and stopped drinking my 6 Mountain Dews a day, which so many young computer scientists did when we were trying to get our programs to run. And maybe I could have avoided that. So the goal is here to learn from electronic health records to make predictions of future clinical events, ideally in time to intervene. When we get the data, electronic health record software is really optimized for fast updates and transactions and reporting. But by the time I get the data, it looks kind of like this, slightly more complicated, but really not much more complicated. There's a table for demographics, a table for ICD coded diagnoses, table for labs, vitals, prescriptions. I ran out of space, so I'm not showing you a table for procedures, but pretty much there's much more in the record, but pretty much this is what we use for the clinical history. Of course, a big challenge we can talk about many challenges, and I'll be happy to talk in more detail about these, but one big challenge is that patients choose to come into the clinic when they want to, and unless you're in Framingham, they're not coming in regularly and getting all the same things recorded every time they come in. So most of the information we care about is missing. Often these are used for billing purposes. So just phenotyping or determining if somebody really had the event that's coded for can be a challenge. So a number of real challenges. Machine learning is pretty good at dealing with noise. So for now, we're going to rely on machine learning's ability to deal with the noise. For some of the approaches that we'll talk about, the timing of events really matters. So here the data is shown as a relational database. That's the format I usually get it in. Many of you get it in that format. But you can also think of each patient as an irregularly sampled timeline. So across the top, I'm showing event types as A, B, and C. These are times when things get recorded in the record. We assume that the event happened the same time it's recorded, but we don't know that. All we really know are when things are recorded. And then I have underneath this an alternative picture of the same timeline. Of course, we really have more on the order of 100,000 events that might be recorded, possibly rather than just 3, as shown here. But of course, as you know, most of our fancy machine learning algorithms, whether they are deep neural networks or support vector machines or elastic nets or take your pick, most of them don't assume that the data look like this or that they look like this. They assume that they look like an Excel spreadsheet or a single table of data. And so that means we either need to change our algorithms or we need to change our data. And most often the easiest approach is to change the data. So here we've summarized a clinical history for each patient. One patient is on a row. I've just called them P1, P2, and so forth. We summarize their demographics, their clinical events, and we've picked one feature such as myocardial infarction in the next period of time that we want to predict. And we want to predict it from the other features. Of course, when we summarize, we lose a lot of important information, but this has the benefit not only that we can get the data in a single table, but there's one row per patient and the fields are nice and aligned. So for one patient, if we look down the third column, then we can see their ages all aligned and we can run our decision trees, random forests, deep neural networks, SVMs, whatever on that data. Of course, the real reason we're running the machine learning, which hopefully you can see my cursor, which I'm showing here in this middle box, is really, the motivation is really over here on this rightmost column, where a patient comes in possibly with our having genomic data represented by G, clinical history data, C, maybe even exposures, environmental exposures, and so forth represented by E. And we can predict future events for that patient or predict response to treatment. Maybe there are 3 possible treatments we can consider today for this patient, and we can predict adverse events or efficacy for each of these treatments in order to make personalized or more precise decisions individualized treatment planning, individualized treatment response prediction. But to get the kind of model we need here to do this personalized or precision medicine, we really need to have data on a lot of other patients where we have the same information, genetic, clinical, and environmental, and they already had this treatment. And we saw what happened. We saw the supervision or the response. So we can use machine learning from that historical data to build these predictive models. Of course, we've talked about some of the problems. Other problems are that new treatments are always becoming available, standard of care is changing, coding practices are changing. And so the data and even the concepts we want to predict are changing with time too. So a number of challenges that we face. I'll start with much of the data and experimental results that I'll talk about are with data that came from the Marshfield Clinic. As Anita said, we were down here in Madison, but up here in the center of the state in Marshfield, they had an electronic medical record that goes back more than 50 years. So we had a total of 1.5 million patients. Some of those patients are just in the record once or twice, but about 1 million of them received most of their care in the Marshfield Clinic system. And then there was also genetic data for about 20,000 of those patients. Okay. So I mentioned that atrial fibrillation is a big interest of mine. So when Umberto Vidier at Marshfield said, let's try to predict atrial fibrillation or flutter, AFF, shown here in this dark blue, I said, sure, I'd love to do that. I think you're all familiar with ROC curves where random guessing or area under the curve of a half would be this lighter blue line. With atrial fibrillation or flutter, we could predict which patients would experience this, making the prediction a month ahead of time. We could predict that with an area under the ROC curve better than 0.7, as shown here. We thought we could predict stroke among patients in AFF better, but it was harder to predict, as shown here. But 1 in 3 year mortality for those patients who stayed in AFib was a little more predictable, as shown here with the ROC curves. You know, I was fortunate when I had my AFib event that that after about 48 hours in the hospital, my heart rate converted back to normal. And there's certainly family history for me with AFib, not at age 34, but at some point. So I may find myself with this again, and these other predictions could be very important and relevant for me. Let me stop there just for a minute and see if anyone has questions so far. If you have a question, please feel free to unmute and just ask me.
Yeah, I don't see anything on the chat, David. So maybe if someone has a question, you could just speak up.
So I'll just say, and feel free to interrupt me at any point, but I'll just say, I think many of you are also working on these same sorts of problems, maybe with other outcomes that you want to predict. And you've encountered a lot of the issues that we encountered. We realized that, you know, a dozen years ago, or actually 15 years ago, as a machine learning researcher, when I started working with EHR data, I thought, I want to know who had AFF. I'll just look at the code for AFF, the ICD-9 at the time, code for AFF, and then I'll know. Similarly for myocardial infarction. But of course, the code might get entered in the MI case just for billing for a troponin test, and then it doesn't get removed. So I learned all about the phenotyping problem. And before I want to predict who will have an event, we have to predict, in air quotes, who did have the event, or a kind of phenotyping problem. So I think many of you are working with these same kinds of tasks. These predictions were with random forests, many of you using random forests, many of you using SVMs, logistic regression or lasso penalized logistic regression, deep neural networks. Yeah, please.
Oh, sorry. Regarding what you had said, you said it's that what's in the data as structured in the EHR is not optimized for machine learning algorithms, et cetera.
That's right.
do you have any transformation of the data, put it in a data set so that it is more optimized for machine learning? What is better than how it's structured in the EHR right now? And does it make sense to transform it into something more optimal?
That's a great question. Thank you so much, Paul. So let me go back and say that my prior work, what kind of brought me to the EHR was my prior work was on machine learning algorithms, especially tailored to this kind of data, to relational databases. And we did see some benefit in running those algorithms, but they take forever to run. And remarkably, we found that random forest performed almost as well if we did the following transformation. So what we did was for every ICD code, we took that one feature and created 4 features, which were how many times did the patient have this code entered? Of course, we don't know how many times they had the event, but how many times did they have this code entered in the last 1 year, 3 years, 5 years, or ever? And your timing might be different if you're trying to predict something else, but we found those timings work pretty well to kind of summarize the clinical history. We did the same thing for procedures and medications. For labs and vitals, of course, things that have continuous values, we used mean, max, and min values to summarize rather than counts of the events. So it's a pretty straightforward summarization. It certainly lost information, but it allowed us to go from this more complicated form of the data to this form that let us run much faster algorithms like random forest that could still capture intricacies like interactions among the variables, but do so much more quickly and could still maintain most of that predictive accuracy. I'll talk later about algorithms that also use this temporal format of the data, but for now we're talking about this format with the summarization I just described. But thanks so much for that question.
Thank you.
And
Hi,
then if
David,
oh,
I have a question. This is
yes.
from this morning we met.
Yes, thank you.
So you presented AUC. My
Yes.
question is, do you have in your practical work to come up with a threshold to say
Oh, great.
high risk, low
That's
risk?
a great question. I really don't, but let me talk around that for a minute. So for atrial fibrillation, we might think 0.7 is not super exciting, but actually, if you look over here if you can see my cursor, if you're over at a recall of 0.3, you have a false positive rate less than 0.1, and if your intervention is to tell this patient, you should decrease your stress for a week, take a vacation, and maybe take an aspirin every day or cut out your caffeine. If somebody could have told me that, I almost certainly could have avoided my atrial fibrillation event. And so if the intervention is low cost, low risk, like that, then operating somewhere here where you've got a really high true positive rate, even though the false positive rate is non-negligible, that could be very reasonable. If this is a really high risk event, but it's an even lower cost intervention, you might even want to get a higher true positive rate, even though lots of patients will unnecessarily be getting the intervention. It really depends on the cost benefit for the event and the treatment or the intervention. I don't have a general way of choosing that operating point. Since you mentioned it, though, I will say also, I've been excited to see a change recently in medicine that was something we were doing in machine learning a lot 20 years ago, which is moving from ROC curves to precision recall curves. They have a big disadvantage in that the area under the curve is very sensitive to your data skew or the either the prevalence or the incidence of the event. But for example, in measuring search engine performance, like with Google, we use PR curves rather than ROC curves because the true events are so rare compared to the false events. And so I do also often advise using PR curves as well as ROC curves, and that can help us pick our operating point sometimes a little bit more effectively. But that's a great question.
Thank you.
Thank you. So for today's talk, though, I'm going, even though I'm a big fan of PR curves and area under the precision recall curve, which is more or less equivalent to something called average precision, if you're familiar with that. For today, I'm mostly going to use AUC ROC. So we got to thinking after we had run about 10 of these or 12 of these predictive tasks, we wondered, well, it would be nice to have a snapshot of how well everything could be predicted at some period of time, like 1 month or 6 months. I'll get to that, but maybe let me briefly say first, we were surprised also that for many of our tasks, when we added the genetic data didn't help our predictive accuracy. We thought the genetic data would really help immensely. Exceptions were breast cancer, age-related macular degeneration, and warfarin dosing. But for MI, for example, we saw the same significant SNPs that everyone else saw in our genetic data, and yet adding them didn't help the predictive model. And we weren't sure whether that was because by the time you have the whole clinical history, you already are seeing the effect of those SNPs on blood pressure and LDL, on cholesterol and so forth, or whether it was because we only had genetic data on 20,000 patients, so we had to reduce our training size down from 1 million to 20,000 in order to use the genetics. So I'll talk a little bit about that as well. But let me say now, let me go back and address this question. How well can we predict everything that has an ICD code? So we started doing this in 2016. So I'm talking about ICD-9 codes for now, but you can do this with ICD-10. This histogram here, or it's actually a kernel density estimation, it's kind of smooth, but this blue one that I'm showing with my cursor is actually, this is showing a set of areas under ROC curves for more than 4,000 different ICD-9 codes predicted 1 month ahead of time. So what we're really saying is if we're censoring our data 1 month earlier, and we're predicting in a month, will this person have the event or not, the average AUC is above 0.8. If we try to go 6 months in advance, we lose some accuracy, as you would expect. But even at 2 years in advance, we're above a mean AUC of 0.2. Of 0.7. And because this was marsh-filled with 50 years of EHR data, we could go all the way back to 20 years in advance. And we're not getting to use a question of, have you had this before? Because we're predicting first occurrence of the event. And we're actually using our controls age and gender matched. Age and gender still play an important role, but if you just use that variable, you wouldn't split on it at all at the top of your tree because we've controlled for that. Of course, you could say, well, predicting precisely 6 months in advance is a little artificial. So what we did also is we said, okay, let's grab another 10,000 patients we didn't look at all. Let's train and cut off a year before and just predict prospectively who will have the various events. And so now this is a smaller set of patients, so it's worth doing a 95% confidence interval. But this is showing our prediction over the next 1 year period who would have this event. This is showing our AUCs across these same codes and the lower and upper bounds on this. Any questions about that so far? Because that's really just to set the stage for my next point. While I give you a minute to think about questions, let me also say, I'm not claiming that we would want to translate every one of these predictive models into the clinic. When you look at them, a lot of the time they're saying things that the doctors would already know. So it's remarkable that we can predict, let's say, tick bites. There's an ICD-9 code for insect or tick bites. It's remarkable we can predict that better than chance until you look at the model, and it can't use that same code earlier because this is first occurrence, but it uses lots of other related codes that show you this person's spending a lot of time outdoors. And so I'm not arguing every one of these should be translated into the clinic right away, but I am arguing you could then look at these and find predictive tasks where you get a high AUC and you think there'd be big impact to predicting. But also it's going to let us answer some general questions like the one I'll address next. So let me go on to that and just interrupt me when you think of a question. At Scott Hebring's suggestion, Scott's a collaborator of mine at Marshfield, our student Xiaowan Huang worked on constructing, not with machine learning, but hand constructing a model that could build family pedigrees. So this is de-identified data, but it's de-identified in such a way that we could still say when two people have the same last name, even though we don't know what that last name is, and live at the same address and have the same responsible payer for their bills over a 3-year period or a 5-year period. And that might be evidence if their ages aren't too far different, that maybe they're siblings. And so we can use some logic. I won't get into all the details of that, but to build pretty accurate family pedigrees from the EHR data. We published this in Bioinformatics in 2018. Nick Tatanetti published something similar in Cell around the same time. And so Xiaowan now has published in Bioinformatics a publicly available software system that can let you use either of these packages or merge information from them. Nick relies on different types of information than we do. He relies on self-reported relationships, whereas we're relying on things that are just in the EHR for everyone, even without any self-reporting, fully de-identified. But it lets us build these family pedigrees, and thereby we can build automated family histories for everyone for every disease, without it, even in cases where we don't carefully interview all these people one-on-one to get their detailed family history. And just to cut to the punchline, let me show you this, this figure now. Across the top, I'm showing you essentially the same rightmost histograms that I showed you earlier. I'm showing you 1 month, 6 month, and 2-year predictive accuracy. And underneath in the mirror, almost what would be mirror image, I'm showing you what happens if to those 100,000 features that came from the EHR data, what if I just added one more feature, one more variable, which is at the date I'm making the prediction, did this person have another family member who already had this diagnosis? Is there not a family history of this disease? And you can see at the 1 month prediction, it helps, but only a little bit. By the 2-year prediction, having that family history is helping. It's helping significantly in every case, but it's helping quite substantially by the 2-year in advance prediction. So this is telling us that across all these diagnosis codes, there's a lot of benefit to family history, even though we didn't really see a lot of benefit from individual SNP markers in most of our predictive tasks that we were doing one at a time earlier. Let me pause again there to see if anybody has a question. Any questions so far? And I realize now when I'm sharing my screen, I always use my computer to tell what time it is. I can't tell. Can anybody tell me how much time?
You are at noon.
Great. So I have
you
another...
have half an hour. There is one question in the chat.
Okay.
Not related specific to this. Maybe you can address it at the end as well.
Sorry, what was the question?
The question
I can't
was,
read.
how about models discrimination and calibration besides the ROC? But it's not really related to this, so we can address that at the end.
Okay,
perhaps.
we'll come back. Thank you. Thanks. Okay. What we noticed when we looked closely at these predictive models, especially with our collaborator at Marshfield, Michael Caldwell, a lot of times the best predictors are not really causes, and beta blockers and myocardial infarction are a classic example. The beta blockers are just telling us the clinician already thinks this person's at risk of an MI. They're certainly not causing the MI. To tease the causes, very often we're really interested in the causes, and to tease those apart, we need to solve the impossible problem of answering counterfactuals from observational data. Answering counterfactuals is usually impossible. We're saying, you know, what would have happened if President Kennedy hadn't been shot or assassinated or whatever, and those are impossible to answer. We get at that information normally with randomization in clinical trials, so we hope with a big enough set of patients and randomization into treatment that that we still don't see what would have happened to this specific patient if they'd had the other treatment, but with randomization, we feel like we can get at the counterfactual information. But often we want to work from the historical record, because the clinical trial may have 1,000 patients, but there may be millions in our record who have had a particular treatment, and we can get a lot more information that way. And so when we're doing pharmacosurveillance, when we're asking about adverse drug events or drug repurposing, we really want to answer these counterfactuals. And we know that some algorithms are better than others. And my research group, like some others, our approach is actually to try to change existing machine learning algorithms into better causal algorithms, causal discovery or causal inference. One approach that many people take, again, everything we talk about will be imperfect. We'll have to make a lot of assumptions because this is in general an impossible problem, and yet we're going to work on it. People are going to analyze observational data, so we want the best algorithms we can get. One clue that people often take is from the temporal ordering of events, because unless someone can build a time machine, we're pretty well convinced that later events can't be the cause of earlier events. And so Granger causality, for example, relies on this assumption. So that motivates us to go back to this view of EHR data, where the colors represent different event types and the downward arrows represent when those events occur. When Congress told the FDA years ago, actually, you have to solve this impossible problem. You have to do pharmacosurveillance from observational data. The FDA and pharma and Foundation for the NIH formed a group that many of you have actually been involved with called the Observational Medical Outcomes Partnership. There's also the Sentinel Initiative, and OMOP has given way to OHDSI or Odyssey now. They decided we need to evaluate these existing methods. So let's come up with a list of drugs on the left or drug classes and a list of events on the right. And let's set a challenge of lining them up. And let's ask how accurately we can line these up. And so here were OMOP's outcomes, health outcomes of interest on the left, labeling the rows, and drug classes of interest across the top, labeling the columns. And the red boxes are cases where from the drug label, you can see that we know the drug can cause that event. The green boxes show the drug is known to help prevent that event. The remainder are potentially negative adverse drug event pairs, where we think the drug does not have an effect on the event. Although in some cases, for some of these, there is some evidence. So the blues were OMOP subsampling of these potential negative pairs that they were pretty confident were really negative pairs. So the task is for now a causal discovery algorithm or a machine learning algorithm that's been modified to be more causally accurate, which is our goal. The task is to take all 100 of these drug condition pairs and rank them from most likely adverse event down to least likely. And then with this ground truth in red and blue, we can compute an ROC curve and an area under the ROC curve. Now, this is very different from the ROC curves I was showing you before. Anytime we have a bunch of labeled data, we can do cross-validation, or we can do a single train test split, train on the training data, and then evaluate and build an ROC curve from the test data. For causal discovery, this is much tougher because now we're asking how well do we recover the causal ground truth? And we often don't know that. So this put us in a special situation where we did have a causal ground truth. Now, I should say people have gone back and criticized various aspects of this ground truth. Certainly, it would be nice if it were larger. We could look at any one of these pairs and raise questions, but overall, it gives us a rare situation where we can take real world data and evaluate a machine learning algorithm or causal inference algorithm for its accuracy at causal discovery rather than just at prediction, which is what we often really care about, the causal discovery. And I certainly personally learned a lot from this evaluation, which I'll tell you about in just a minute. As we talked about the challenges with EHR data, even if you have your machine learning algorithm up and ready to run, there's 90% of the work is just converting the data into the forms you can run machine learning. The same is true now for causal discovery. What we really get are drug prescriptions shown here for say warfarin across the top. And we may take dose into account, but just because we have drug prescription doesn't mean the patient really took that drug every day. We might not know how long their prescription lasted. Maybe not with warfarin, but some of these drugs, people are encouraged to buy a larger pill and to do pill splitting because it's cheaper. So it can be pretty tricky just filling in from the prescription data the actual days of exposure to that drug. And then intuitively, what we're going to be trying to do is say, look at an event like bleeding and when it's occurring, and ask if that's correlated in some way with the drug exposures, believing if we're careful to use time, we might get more insight into causation. Now, a lot of the very elegant work in causal inference actually doesn't rely on empirical evaluation. We have proofs, work by Judea Pearl and Donald Rubin and Jamie Robbins and others. Lets us say, under these assumptions, under these conditions, we're guaranteed to make the right causal inferences. And I love that elegant theoretical work. But what OMOP showed us, which we kind of suspected before anyway, is a lot of times in the real world, those assumptions are wrong, like there are no unmeasured confounders or things like that. And so in the real world, what OMOP showed is that other methods outperform those with the theoretical guarantees. One example was self-controlled case series, where we said, okay, for this particular patient, there are days she's on warfarin and days she's not. Let's look at whether the bleeding always occurs while she's on warfarin. And if so, that's evidence. Maybe doesn't guarantee the warfarin's causing it, but it sure is evidence. Now, warfarin's an easy case because we know it's a blood thinner and it can cause bleeding, but some of these can be much, much tougher. So this is giving self-controlled case series as an example. This is a particular algorithm called multiple self-controlled case series, which is learning a linear model to predict the event based on the various drugs that the patient is exposed to. So the multiple comes from considering many drugs at once. And the magic, I'll say, that lets SCCS or self-controlled case series work is that we're only looking at patients who are exposed to this drug and have this event. And we're just focusing in on when they have the event. How often are the events for these patients during exposures versus not? And so every patient has a different baseline risk of the event, but because we're using each patient as their own control during the non-exposed times, we're kind of adjusting for that confounder, even though it's unmeasured, even though we don't know that patient's baseline risk. So we learned a lesson from SCCS. And when my student Charles Kwong was in a meeting with me, my collaborator Jamie Thompson called up and said, somebody's using our pluripotent stem cells to find if drugs on the market for other reasons seem to give glucose control, seem to lower blood sugar or fasting blood glucose. And then they're evaluating those predictions using the electronic health record. Couldn't we start from the electronic health record? And so Charles and I said, yes, we could. And I proposed an approach. So if you look at this patient here across the top, this patient has fasting blood glucose measurements at different days. Those are the up arrows with the numbers. The patient has different drug exposures. Also, we could make use of different ICD codes that get entered. And we have age information about the patient. And we'd like to get insight into whether this drug is causing a change in glucose. So my big contribution to this work was to give Charles an approach that worked really badly. I said, let's just find all the patients who went on this drug and let's take their last glucose measurement before they started the drug and the first one after. Let's compute the difference and average that over all the patients on the drug and rank the patients by those averages. And then we came up with a list of drugs that I took to Michael Caldwell. Michael brought us a ground truth list of drugs that are known to alter blood glucose. Some, that's their purpose, like insulin and metformin. Some it's known as a side effect that's been found later, either good or bad. Some are things like glucose, which when you're prescribed insulin, you're also given a glucose prescription in case you get too much insulin. And so we colored the drugs in green that in fact were known to lower blood glucose, and in red, those that were known to elevate blood glucose, like glucose. And among our top 40 drugs, half of them were red. We were being confounded very terribly. So Charles then said, okay, let's calculate a baseline glucose. If people were on no drug, let's estimate a baseline glucose for every patient. And that helped. That got rid of about half of the red. And then he said, let's do what's in this formulation here. People's fasting blood glucose, like their cholesterol and their blood pressure, change with time. Let's actually do this. The top line I'm showing here is just standard ordinary least squares linear regression, just standard linear regression. Y is the glucose, and betas are the coefficients on the drugs. Let's just do a standard linear regression, but let's replace the intercept by allowing every patient to have their own intercept or their own average blood glucose if they were on no drugs at all. Then let's have a lasso penalty. And let's also say there's a big penalty every time we allow that patient's intercept to change. And that's that penalty here. So you could explain all the patient's measurements just with this intercept that we're completely guessing, their baseline glucose. But you pay a penalty for changing that intercept over time. And so if you've got a bunch of patients whose glucose dropped after they went on the same drug, you put that on the drug and you pay and you avoid this penalty that I'm showing here. If they were all on different drugs, you have no choice but to put it on changes in their own individual glucose levels with time. And when we did that, I'm showing you on the right the much better result we got after my naive approach when we had a patient-specific baseline, and I'm showing you on the left the results after Charles's approach. We got rid of all the red in this case empirically, and that provides evidence that the things in white here, some of them you would never give to control blood glucose, but some you might. That provides evidence that they're actually helping control blood glucose. And in fact, we found some literature support for some of these, like some of the SSRIs, after the fact. Charles then took this back to the original OMOP task, which I had shown you before, where the response is binary. Either you have the adverse outcome or you don't. He took it back to that task with the many different settings that OMOP had for the task, like how long we anticipate a drug exposure to be after prescription, how long we anticipate a risk to be after the exposure stops. And across all these variations of the experiment, found that his baseline regularization also substantially improved over SCCS, which was already arguably the best performer for this task. Let me stop and ask Anita again how much time I have left. I'm sorry, I have to keep asking you that.
It's 12:18, David.
Okay, so I need to wrap up pretty quickly.
Yes.
I want to get to my punchline now, which don't get too bogged down in the details, but I hope you get the big picture of this. OMOP was a very special case where we could empirically evaluate causal discovery, and we usually can't. And even for supervised learning, where it's much easier to empirically evaluate, it was found to be very useful to have a theoretical formulation. And Les Valiant created something called probably approximately correct learning, where he said the goal is to get data, a training data set block D from some distribution script D over possible data points, labeled according to some target concept, and to model a learner that produces a hypothesis little h that captures the target concept little c from our big concept class big C. And he said what we want to do is minimize the error. So if I'm showing the target concept C, the hypothesis H, we want to minimize the shaded region. And we'd like to prove that our algorithm could do that. So for any possible class C of target concepts, we're going to say an algorithm L can pack learn C using possibly a different hypothesis class H. If seeing a polynomial amount of data with high confidence, it gets high accuracy or low error epsilon. And it gets more time and data when the error has to be lower. So it gets time and data polynomial in 1 over epsilon, 1 over delta, the confidence, and the number of variables, and C, the size of C, the unknown target concept. And then this is a model that you prove theorems in. You prove that this algorithm will pack learn decision trees. In fact, pack learnability decision tree is still an open question, but you prove that that you can pack learn a given target concept. We'd like to do the same thing for causal discovery. And I want to close today by pitching such a model to you. There are already beautiful, elegant models by Pearl and Rubin and others for causal discovery or causal inference. What's different here, I'm not trying to replace those, but I'm trying to make the computation piece front and center in this model. So I'm saying you have two models that are generating data. And in computer science, we always use Turing machines. That's what these models will be. And Turing machines generate strings, but you can think of these as the rows in our Excel spreadsheet or our feature vector. These are just our feature vectors that represent our examples. The learner is going to see a data set drawn from one of these, and it needs to say which one it came from. And it needs to get time polynomial in an amount of examples, polynomial in 1 over epsilon, where epsilon's the error that we're allowing. So in case this is too abstract, I'll give you a concrete example. that capture some of what we already talk about in causal inference, for example, with Bayesian networks. So we have three variables, A, B, and C, and we're not sure whether A has a causal influence on B, as shown on the left. A might be a drug. A might be the drug Vioxx back when it was on the market, and B might be myocardial infarction. We want to know, the question is there an arrow here or is there not? It's an important question. And under certain natural assumptions, you can prove a PAC causal discovery or a PACC result, a positive result for an algorithm that's already in wide usage for learning Bayesian networks. But I'm going to just summarize for you and tell you that SCCS, which works so well in the OMOP evaluation, had no such formal result. And now under the PACC model, even in the presence of an unmeasured confounder U, as shown here, SCCS provably lets us accurately determine whether there should be an arrow from D, the drug, to E, the event. So we're able to prove positive results for SCCS and also instrumental variable approaches in this model. And these are the first theoretical results for SCCS. But to prove the result, you have to do something very interesting that people weren't doing during OMOP. And we think it makes the approach even better. And that is, you've got to throw away some data, which is usually a bad thing to do in machine learning. But the key that makes this work, that allows you, this unmeasured confounder, to be influencing both D and E and still not mess us up, the key is to say, we're going to make sure every patient has both exposed and unexposed time, that it's the same amount of time for that patient, and it's the same amount of time over all the patients. And to ensure that, we may have to throw out some patients with very little exposure, and we may have to throw out some time, some data for some of the other patients, but it lets the proof go through. I think I'm going to, Aneta, am I out of time or do I have one more minute? Sorry.
You have 6 minutes.
I want to
But if
leave
you want to
time.
allow for questions, just 1 minute.
I want to allow for questions. So let me take 1 minute to tell you, also, let me just jump ahead and tell you about another application that's of great interest to people. So this has happened to me, it's happened to my kids. They're on a drug that works well. A generic drug comes on the market. Is the generic drug just as good? Is the generic drug causing any adverse events that the brand drug doesn't? Usually no, but people are very worried about this. And so, so we worked really hard on this problem with Marshfield, and we said, we don't know what the generic drug might be causing. So let's try to do machine learning to ask if we can predict, in air quotes again, backwards in time, predict whether the patient during this time window was on the generic or the brand. And if we can build a model that predicts this accurately, better than chance, then the generic is doing something different. We ran this approach and we found it was really great at finding idiosyncrasies in the data. Like there was a drug that right when the generic was released was the same time Marshfield started transmitting prescriptions electronically. So it got a really accurate model that said, if this prescription was transmitted electronically, then you were taking the generic drug. And so there were all these temporal confounders, like changes to the health system. And to get to the punchline, I'll say that, that this PAC model suggested an algorithm, a different use for those who are familiar with inverse probability weighting and propensity scoring, a different use of that technology to do propensity scoring to capture time and to adjust for confounders that were changing with time, which is a huge problem for these causal discovery methods. And so the approach is to essentially first predict timing, adjust for that, and then use this approach that we're talking about with discovering previously unanticipated effects of generic drugs. So I think I'm going to just jump ahead and show you a conclusion slide. This is work in progress now based on what I've told you about, trying to extend methods like Charles Kwong's method to approaches that can capture drug-drug interactions like deep neural networks, and trying to evaluate this within that pack discovery model. And I'll stop there. Thank you.
Thank you so much, David, for this great talk and showing all this wonderful work you've been doing. We have time for a question. There was one on the chat, David, if you want to quick respond that.
I can see chat now that I'm
Yeah, so how about models discriminating calibration besides the ROC?
Okay, let's see.
This is a question by Christina Barboy.
Okay, let's see. Got it. How about modeling discrimination and calibration besides AUC-ROC? Yeah, so my favorite approach actually is, no approach is perfect, let me say, but my favorite approach is precision recall curves and area under the PR curve. But there's some details you have to deal with. One reason I didn't use AUC-PR when I showed you those histograms across many different tasks is the good thing about AUC-PR is it's sensitive to the real world prevalence or incidence. It's sensitive to the real world class distribution for what you're trying to predict. But the problem is, because of that, if I tried to average over many different tasks, they all had different class distributions or different class skews. And my student Kendrick Boyd had shown years ago that depending on the class skew, you get a bunch of AUC-PR for free. In other words, it doesn't matter how badly you try to do, there are some regions in PR space that you just can't get into, in contrast to ROC space. And if you have unskewed data, if you have equal numbers of cases and controls, let's say, that region that you get for free is really large. It's like a third of your whole space. And so you might think that you got better when you downsampled your negative class or your more common class maybe, but all you did is you made the problem easier. So you can't really average over multiple problems with AUC-PR, which is why I stuck with AUC-ROC there. This is still a hotly researched area of machine learning methodology, better and better ways to evaluate how well our discriminator is working. So thanks for that question.
So David, we are about time, but I think Jared has one final question for you, if you don't mind answering.
Okay, great.
Hi, thank you so much for your talk. It was incredible. I have one very quick comment and a question. My name is Gerard Hills. I'm a dual PT Mock and Clinical Informatics Fellow here. And my work is in looking at patients with sickle cell disease. And we've kind of had some issues with that gap between pediatric to adult care with the work they're like having a worse clinical outcomes and increasing in mortality. But we don't exactly know why. And so I think that maybe using some of these tools that you have, like PAC, being able to kind of get at a little bit more causal relationships might be something interesting. So
I'd love to talk more about that.
Email you.
Fascinating. Yeah.
And then also my question was, did you know, do you think there would be any utility in being able to use PAC for clinical decision support with symptomatology? For example, with patients in the hospital, there may be multiple reasons why someone would have a fever, for example, and we're using our clinical judgment based on what we know. But is there a way that the EMR would be able to support us and say that, like, these are we have our top things that we think are related to this, and then the computer would be able to give us a breakdown in percentage as to like what they think, what it believes would be the most likely thing, and as an additive to support the clinician. So I don't know. I
would love if we can do that. I think there are going to be some tasks where, because the EHR data are pretty sparse, there are going to be some tasks where The model does significantly better than chance, but it doesn't tell the clinicians anything they didn't already know. I think that will happen a lot. But I think the really interesting cases are where we can find that the model is at least as effective or maybe more effective and is teaching them something they did not already know. So, one example that gets a lot of attention now is using images to recognize melanomas using convolutional neural networks. And are there things like that where we can have a positive impact? And I think especially cases where there's much richer data in the EHR, like inpatient kinds of things where the data is being continually collected, or as we move to more of a situation of mobile health and there's more continual collection of data, I think we'll see more and more cases where the computer can really help the human. But I think there are some cases now, and that's the big challenge now is often where the computer can do better is with a deep neural network, but then it's hard to tell the clinician the basis for the reason, which makes it hard to convince, I think, the clinician. So explainability of these models is really important too. Thanks so much for that question.
Yeah, thank you, Gerard. Thank you, David, so much. This was great. Thank you, everybody, for staying along with us, even past the hour. We appreciate you coming here and sharing your knowledge with us. I hope everybody has a great day and hope we can all collaborate in the future again, David.
Thank you. I'd love that.
Bye, everybody. Have a great
Bye-bye.
day.